like from the huge research in the multimodal AGIs. They try to integrate this knowledge from text, audio, graphics, video to enable diverse applications like language learning assist, some gaming like scenarios, some interactive learning applications, etc. And it also have broad like applications in the medical domain. For example, like for the Alzheimer's disease or the, okay, yeah, let's continue. Like for example, the Alzheimer's disease or for the cancers, we have different measurements. For example, you will have the clinical, like natural language descriptions. You will
可是我只有4000多块钱，
CT, etc.
没有秒钱，
Also have some
财
genetics,
产不能分散。
either like ion expression, right? Also some like a mutation, like its effects on the drug response, etc. And you will also have the biospecimen kind of measurement. So how to integrate such multimodality informations to make the prediction, to modeling the disease behaviors on the lines? It will be like a $1 million question. However, there are a lot of challenges in the multimodal modeling. Today, I will show you one of the challenges. This modality. So let's zoom in a little bit to a very popular or representative data set, Alzheimer's disease, with admin. And then you have four modalities, clinical notes, biospecimens, images, and genetics. They have different quantities. You may be curious of why it have different quantities for different modalities. This is mainly because for different patients, sometimes you only have like a few modalities, few measurements available. For example, for like a patient in this cycle, you will only have the imaging, you will only have the imaging modalities here. And then if you patient lying in this like regions of the VM plot, it will only have imaging and clinical notes like a measurement. And however, other kind of modalities. What kind of things, what kind of issues will this phenomenon brings us? First one, probably will fail training. Because imagine like for the whole patient, you measure like a 10,000 patient, but the unit, the patient has the full modality measurement, maybe only 1,000. So the training data will be limited and it will constrain the power of your training model, learning model, right? The second issue will be, it will fail inference. So imagine in the training stage, you build a model, can modeling multimodal measurement and for the predictions. However, you want to deploy it on some like other place, other hospital or other rural areas where cell hospital or cell like a medical service can only support you like medical imaging data. So which means in the inference time deployed stage, you only have one measurement. How to make a model, multimodal, like AI model can still predict in this scenario with only partial observable information. In order to tackle these two challenges, like in this community, a lot of research is conducted to try to see whether it can solve this like issue. So there is like one group of research is try to like directly train with some mask in an input domain. Basically, if something is missing, they just will put it here like a placeholder, which will be a mask. Everything will be 0. And just input the models to enable the multimodal training with missing information, missing modality. Of course, it's not good because your model will learn some very weird patterns with whole like 0, whole 1 masks. Second group of methods, they try to improve a little bit on top of the previous one. They will use some learnable invariants. Rather than put like a fixed static 0 or 1 mask, they will use some like random initialize the vectors and make it learnable during the training. And second group of they use like a non-distillation for sure. For example, like you have like 4 modality multimodal like AI models. Whenever deployment time, you can only support like 2 modality. So I use non-distillation to borrow knowledge from the 4 modality AI models to train a smaller model with only 2 modalities. Additional training costs for sure. And the last one is a very new like papers in the medical domain. basically say we'll try to like diagnosis whether this application like need certain measurement. If it's application like a skin disease diagnosis, it mainly only needs image modality. So they will just borrow an image single modality models. And as the lead, basically we will mainly rely on these predictions. And for other modalities, it can generate some predictions, but it will assign it like a low confidence. If one modality is missing, it's fine. Because for the skin disease, we say mainly focus on the like imaging modality. However, all this method didn't actually like doing the flexible modality learning. They try to avoid these issues by looking for other alternative method by sacrificing additional training costs or leveraging some domain knowledges to limit the search space. So the last one will be image modality generation method or modality imputation, maybe more familiar term to people from biostatistics community. So first one, they try to learn some modality specific embeddings and learn some modality shared embeddings. If modality is one modality is missing, they will use the modality shared embedding to as a replace for that modality. And the second group of research, they mainly use the diffusion-based models to condition on the observed like information to generate missing informations. However, we want to tackle these issues from a more scalable, more efficient way from the architecture perspective. So hopefully, by enabling the flexible modality learning, we can incorporate all the patient samples with only partially observed like measurement. We hope rather than building a model like most of existing methods only train the models with unit of the patient. We hope we can leverage all the patient measurement in different like regions in this VM plot. They can only have like one image measurement, or maybe only have image and clinical notes measurement. We hope we use them all. How can we do that? Like we will introduce a new framework to enable it. But first of all, let me introduce a little bit for the background for our method. Like our method will mainly developed on top of the mixture of experts. So what is mixture of experts? Yeah, it have like a very broad definition. The first work is proposed in the 1987 to improve EM algorithms from in the statistics domain. And later on, the 2017, Google like integrated such ideas into transform architecture and make it like great again in a lot of AI domains. So we will first start from like some illustration. So we have some input. It can be question, can be clinical notes, can be image. We will embed them into tokens. It will fit into some agent. It will be like a routing agent. Such agent can be a model, can be like a lookup table. Basically, it will assign the inputs to the most relevant expert to solve it. You can see like this will have some pre-diagnosis for the patient, and it will allocate to the most related or like effective doctors to solve this patient. So basically, it will activate like 2 to 3 experts to process the imbalance, and later on they will like fuse them together for the final prediction. So we can go through the equations. The x here is the input. Fx will be the expert features. Then I here is the routing policy. Basically, routing policy will take your x as the input and select a few expert if and aggregate their like information together. So the y will be final feature imbalance for the prediction. Okay, then let's move forward to our proposed method. So basically, our method will contain 4 parts. No worries, there are too many informations in the figure. I will go through like one pieces by one pieces. So first part, like we will build a flexible mixture of expert framework. So in this framework, the first things we propose is that we will sorting the data from easy to hard in the machine learning science. So basically, we are sorting the patients with different modalities. If the patient have 4 modalities, we simply have sufficient information for model to learn. So we will learn it first. Later on, we will learn the group of patients with 1 modality missing, have 3 other modalities. And gradually, we will try to learn like a patient with only 1 modality information. We think it's more challenging, more hard.
What are the 4 columns again? It's
4 columns here is,
X-ray or
yeah, this is imaging,
Yeah.
like X-ray or
MRI.
MRI or CTs, depending on different disease.
Yeah.
So in our studies, we focus on the Alzheimer's disease, cancer, and chip X-ray, these 3 data sets, adenine, cancer, and mimic.
And then it's like a
Second one is-
data set.
What?
I'm just wondering, what are the 4 columns? again?
Yes, so first one will be the image modality,
Okay, so image,
and second one will be clinical notes or tabular data.
okay,
The third one will be biospecimen.
okay,
The last one will be genetics.
okay.
Yeah, genetics and genomics data depending on different
So
applications.
lab results would be in the third bucket.
And we, according to this like 4 modality, we ranking the patients if more information we think it's more easy to capture. So we learn in the beginning. Like we gradually learn the hard example with patient with only 1 information, 1 modality information. Okay, so this is actually
Question, the data set you just mentioned, so what is the scale of, in terms of number of patients? They have all of this for different modalities of data. I think
yeah, it's like a few thousand for the adenine. Yeah.
Only adding, right?
Yes,
Yeah.
and for the cancer, it's only less than 100.
And for
for each
me,
level.
I don't remember to have genetic data. Not-
Yes, so in the TCGA, they have like genomics data and imaging data. So in that case, we will only play with the genomics and imaging, the 2 modalities.
For modalities.
Yes,
So any data set has like 4 modalities?
adenine have 4
Adenine.
modalities. Yes, and for the mimic, it has 3 modalities. Thanks. Cool. Okay, so actually, we borrow these ideas from curriculum learning, basically try to let your model learn from easy samples to harder samples. And the second design, we will create a missing modality memory bank. So for each missing scenarios, for example, ICB means the genetics modality is missing. So we will like create a row here. We will learn some embeddings for this scenario. And for IBG means like clinical notes modality is missing, and we will create another like embeddings to learn in these scenarios. So in this way, we will create like a memory embedding bank, and then within this bank, each row will corresponding to 1 missing modality scenarios, and then within this like columns, we will put like 1 learnable embeddings to feed in all the patient samples. The missing information in a data-driven way. Okay, this is the second design. So the third part is that, okay, now we have the memory bank. Basically, for each patient, either for the observed information or the missing information, we will have embeddings to indicate that scenario. Also, we will create some specific expert for each like missing scenarios. For example, for some modules, some expert like ICB, it should created to deal with some missing scenarios where the genetics data is missing. Only ICB modalities are filled. So in this case, we will create a bunch of experts to deal with different missing scenarios. And the last thing in this framework will be allocation. So you have the invariance where it's input. You also have the expert which can deal with different cases. So how could you allocate different input to its associated expert to process the sample, to process the patient information? So this is our last thesis of design, the routing policy design. So this routing policy contains 2 scenarios. If 1 patient have 4 information, which means all the modality have imbalance, we will concatenate them together directly, like select the top 2 most similar or associated expert for deal with this patient. However, if it's like for the missing modality patients, we actually will decompose the routing into two parts. First part, according to the missing information, for example, it's IBG, which means the clinical information is missing. We will find the corresponding IBG expert here, which is specially created to handle this IBG scenario. We will activate this expert. And for another expert, we will use data-driven routing to select like the associated expert and combine them together for the inference, for the predictions, for the missing modality patients, IBG. And this is another example. So if the patient only have like one modality, which is clinical notes, and we will activate the expert only handle like a clinical notes as one expert. And another expert, we hope it can borrow some like cross modality informations, which can be captured in other experts. We will select one more and combine them for the final predictions. Okay, I will stop here like for 10 seconds if I have any further questions. If not, we will go to the experiment
The expert
results.
is an expert model, not an expert person.
Yes, it's expert model. Yes. So if we like think it like a more broad concept, we currently also building some human AI teaming framework. Basically, some expert will be AI models, some expert will be the real patient, like a real doctor. So we can integrate the doctor's feedback and AI's feedback together for the routing, for the prediction, etc. Thanks. Yeah, please.
Tianlong, I have a question as well. Sorry, can you hear me?
More along the lines of conditional expectation. Is that what you're using there? Because you're looking at the expected, like you said, clinical note, given that you have this information, this information, this information. Is that the kind of framework that you're putting this in?
Yeah, thanks. So actually it can have two parts. One part, yes, it will conditional on the missing scenarios. If it only has the clinical observations, which is reliable, others we are generated by AI, right? So in this case, we will condition on this situation, only activate the expert, only deal with it. And another part will be a data-driven part, which means we will leverage the learnable embeddings through the memory bank and use the learnable embeddings to try to search from other experts to see whether we can find another associate or related expert, which is not dealing with clinical, dealing with other modalities, try to borrow some cross-modality information to assist the prediction.
So when you're borrowing that within the columns like you're showing from the other patients that you have in the bank.
So a similar way, but a little bit like different. So we will like find the embeddings in each columns, right? And in each columns we will pass through agent, a router. So this router will be another neural network or AI. It will help you to locate which expert can be more helpful in a data-driven way. So the first piece is analytical, basically based on the observations, based on our expertise. We think like we can use the models only deal with clinical to deal with the patient with only clinical information. The second one will be more like AI-driven, more black box, more data-driven, try to associate more another like expert can help your prediction. Does it make sense? And that actually should capture the overall information from all the patients because it will learn from all the patients.
So let me say another way, what
Okay.
I'm thinking that, are you using information from other patients that have similar information to what the patient in question has? To then, these patients have, let's say, pooled information, right? And then this patient has reduced information. So you're basically looking at the patients with full information and the reduced here that are most similar, and then extrapolating the unknown information.
Yes, exactly. So basically, it will borrow like other scenarios. It can be like with more like a full information. It can also be other scenarios like ICB, genetic signature.
Right.
Basically, like other scenario beyond just the clinical notes. Yeah.
So in my world, and I'm a statistician by training, I do bioinformatics, and our lab's doing more and more with AI. You're creating digital twins, is what you're creating in that sense.
Yeah, we,
Because anytime you're talking about the similarities between the patients that mirror a patient or a case in question, that in a broader sense, you're creating digital twins. So I just bring that up because I had a discussion with Dr. Yang about that. Asking about that question, like, we're doing the same thing, but our languages still need to come together more cohesively,
Mhm.
so.
I have a follow-up question. This is a follow-up question. So, you borrow modality from other patient has the modality, right? But the problem is that the patient can have very different disease. They are very different. For instance, this is cancer, this is diabetes, and the cancer one has all four modality, but you cannot borrow their things to predict the diabetes. So you need to maybe check whether the patients are similar. They are same condition or same age or same risk, some like matchmaking. Then you only borrow the similar patient that match this patient. Then if they have modality or.
currently we only do within disease. We didn't do like
Oh.
across disease.
But even within disease,
Yeah, they all have
you can
difference.
do measures of similarity and variation within a digital twin.
Yeah.
Mhm.
So you can get that with the confidence limit and interval.
Yeah.
For instance, like heart disease, the children and adult are very different. You cannot just you have to also do some matchmaking.
Yeah, so I would say like for this like missing embedding or missing knowledge imputations, there are a bunch of ways. For example, like as mentioned, we can align cell embeddings in the joint unit space and do the similarity calculations to retrieve that patient. Such kind of like explicitly designs is very popular in this domain. So I think they are like quite orthogonal to the, oh yeah, please.
Sorry, I have another question, since you seem to understand statistics as well, which I appreciate. So are you taking into account the different types of missingness, like the missing at random, informative missingness? Because there's different statistical levels to each. I'm guessing not, but if not, that's good, because that leaves some research open.
Yeah, honestly speaking, currently we only deal with like high level missing. We will not care about like a detailed like a missing. Yes,
Why?
yes, exactly. And but I would say this kind of alignment and retrieval method is quite orthogonal to this framework, can be further incorporated and makes like a model more accurate. So it's more like in the model architecture design and the implicit knowledge like learning designs. Okay, let me show you a few results so we can continue the discussions like after the talk. Thanks for the fantastic questions. So like this is the overall results for the atom data set. We do have the cancer results in the appendix, but I didn't put it here. So the first table is a single modality performance with either one of them. And the second table is two modalities with like imaging and genetics. And for sure, we compare across these two tables, two modality can virtual better than like one modality measurement. And compare with different method, all method will like give you a better performance improvement, like 1% or 2% compared to different like baselines in the literature. So each column will be a baseline. So each rows will be measured in terms of accuracy and F1 score. The last column will be our method. So the third table will be like with 3 modalities, and the last table will be with 4 modalities. Actually, there is several takeaways. Let me show you one by one. So first takeaway. If you compare with the last 2 tables with the first table and the second table, like you can see like for other method, it seems like more modality didn't give you better performance. So it actually like refer to another challenge I will briefly go through later in the next slide. It's a modality conflict. So basically imagine you have like multiple modalities. One modality will hoping your model can be optimized in this direction. And another modality will hoping to optimize your model in this direction. If the gradient is larger than 90 degrees, which means that their updated information will be canceled with each other to some degree, and it will lead to optimization conflict. I can show you more statistics like later. So this is why like whenever you directly combining all the modality information to do multimodal learning will not necessarily lead to a good performance. Second one, we can see that although like our model is also influenced with 2 modality or 3 modality. It can be consistently better than other method because in the training we do see 4 modality informations from the patients, right? So it is another evidence to show that we can capture like 4 modality information in the training stage. However, in the deployment time, we can support with partial observable patients in different scenarios, in rural areas, etc. Okay. Yeah, due to the time limit, let me quickly go through some ablation studies. We show like different designs will lead to performance boost, like on top of like the 4 variation. And this is another like ablation designs to show how many expert you need, how many like a mixture of expert layers you need, and how to choose a hyperparameter top case in the framework. And later on, this is expert utilization figures. Little bit like complicated, but let me give you an illustration. So x-axis is a different expert. You can see it's IGCB means 4 modality expert with 4 modality information. I means only have the imaging data set. G means it has only deal with the genomics data information. And we hope like, for example, we hope like for the patients, we care about like clinical notes. Such whenever we have the patients with only clinical notes or have clinical information, we hope it can activate the expert who will deal with the clinical knowledge. So let's see. So first one, the yellow one. Okay, CGI, yes, and also for the this one, BC, it also has the yellow one, which means for the expert we created to deal with multimodal information, like whenever it's related to clinical information, it can indeed be activated for the patient with the clinical information, clinical measurement. So this is another post explanation for the design. Yeah, thank you.
You also have a GI which has no C, but also activates C.
Yeah. So yeah. So another like intuitive explanation will be like maybe like genetics or image data, they convey some information, so can be very helpful for the patients with like only C measurement. So it will be like can be explained like cross modality information.
GI has some, but the GI has a medical like radiology report is text.
G is genetics and I is imaging. Yeah, we think it may contain some cross informations which can help the patients with only clinical data, clinical notes. Yes.
What about conversely? It looked like the C column didn't activate the
Yes.
yellow at all.
Yeah.
What's going on there?
Yeah, this is some like I don't honestly I'm not sure. This is like data driven by the model architecture, but I think like C is activated for like 4 modality learning. Yeah. So I think this calculation is exclude another statistics. So because like for the patients with only clinical information, it will by default only activate the C. So we will exclude this group of statistics out of this plot. Because by design, if it's like utilizing the clinical nodes, we will by default activate the clinical expert. And for another one will be a data-driven learned, like for the AI agent. Yeah, yeah, please.
So on part D of that big figure that we did, this is only one side of it, and the other side you do the C gets C, GI gets GI.
Yes, yes.
Okay.
Yes, there's 2 parts. One part is by default design. Another part is choosing by the AI model. Yeah.
But if you say the image have C can help image to do some prediction, but your image I has no C in there.
Yeah, I would say this can be interpreted as like the patient with genetics information and image information.
But it's purely image, there's no C.
I would say we cannot like conclude in that way, but like from the AI selection statistics, we try to interpret why it can activate in this pattern. Yeah.
We also stack percentages, so I might just not be activating much at all. We don't see much.
Mm-hmm. Okay, so I will go through the last 2 to 3 slides quickly. So beyond the missing modality issues, there indeed have some other challenges in the multimodal multitask learning. So the first one will be modality conflict. As I mentioned, if your optimization directions is larger than 90 degrees, it will it canceled with each other. Second one will be the feeding issues. This is a problem most of researchers will have trouble with. Basically, for complex tasks or complicated modalities, you need like a huge model. For simple tasks or simple modalities, you need a small model. However, for the multimodal method, you have a fixed size. So it can underfitting for complicated tasks or overfitting to the simple tasks. We need a dynamic structures can be adjustable for different scenarios. The last one will be the learning pace. So if one modality, one task only have 100 samples, it's very quickly to converge. If it have like 10 million samples, it's very hard to converge, very slowly to converge. How to synergize the learning pace for the multimodal learning is another problem, because you are always learning it simultaneously. If one is already converged, you keep training it, you will lead to overfitting issues, right? So mixture of experts like actually by additional designs, you can try to mitigate these issues. But I will directly show you the statistics. So you can see here, the yellow histogram and the blue histogram. So the y-axis is the number of situations, is calculations numbers. X-axis is the cosine similarities of the optimization directions. You can see for the vanilla multimodal learning method, most of them is less than 0, which means the cosine similarity is negative, which means the angle is larger than 90 degrees, which means the optimization is a conflict. But if you decompose the parameter space, the VO method, we can alleviate these conflictions and push the distribution from negative central to zero central distributions. This is another reason why our method can perform better than single modality learning. But if you directly combine all the modalities, it can lead to performance degradation sometimes. And third figure show you how it can alleviate the overfitting issues and synergize the learning pace. The last slide I want to show you. This is in the general vision domain. And we try to show some specializations for the expert design. Basically, try to see whether a special group of experts can capture some special patterns in image. Let me show you. This is image classification, segmentation, detection. And then for each block, the color for the boundary indicate like the index of one expert. The content, the color in the box is indicate another expert we select. For each sample, we will select 2 experts. You can see in the image classification, all the background text which have less information will be handled as two fixed experts. We like in the computer vision, we call it like a garbage expert, which will deal with the background text. And for the object itself, have a lot of rich information to select like a very rich combination for the expert. And also for the segmentation detection task, you can see there the boundary for the object is activated the blue like expert. For the content, for the texture or the object, it will activate like a green expert. And also similar stories for segmentations. So this is actually another ultimate goal for the machine learning mixture of expert design. We try to encourage the specializations. We hope some modules can capture A knowledge, another module can capture B knowledge, another module can capture C knowledge. For unseen task, for unseen patients, for unseen scenario, we can compose the learner knowledge in a dynamic way to solve the unseen sample, to answer the questions from the unseen scenario. Thank you. I think that's all. Yeah, sorry for delay for 10 minutes. Okay.
I have a question.
online audience, they have to leave early. I don't see any, okay. So then, if you don't have any question, I will record it, so we will post it on the website. Thank you very much for attending this online talk. Yeah, we can close that.
Okay, thank you.